Hi, let us continue with our lesson series of process synthesis, design and Chemcad simulation of biomethanol production from biomass. In the first 3 lessons, we have introduced the problem and discussed how to build the process flow diagram for Chemcad simulation. In this 4th lesson series, we are going to build a Chemcad process simulation for the given design specifications. We will first look at the design process specifications. Then we will do gasification stoichiometry and perform the stoichiometric reactor simulation. Furthermore, we will look at the water-gas shift equilibrium reactor simulation. Then, we will look at gas processing and cleanup. Herein, we will adopt one of the Chemcad acid gas removal examples for our simulation. We will then proceed to tackle the simulation of methanol synthesis kinetic reactor. Once the biomethanol product is produced, we will look at separation and product cleanup. And lastly, we will conclude the conceptual design phase by looking at the recycle and Chemcad simulation convergence. Without any further delays, let's get into it. Remember, our design problem is that you are required to design a process for the production of biomethanol from biomass through gasification of biomass and production of methanol from the synthesis gas via methanol synthesis process. The final methanol product needs to be of at least 99.5% purity. A rough block flow diagram for the process is given here. Our design problem specifications are given as follows. We are required to design a 500 kilotons per annum plant capacity with an on-stream factor of 0.8, or 80% of the time. In order to simulate biomass, we will be using lignin H, which we are going to represent using this molecule, C22H28O6. Gasifier operation conditions are given here, as well as the methanol synthesis operating conditions. These will remain the same as before, as discussed in Lesson 1. And, for reasons given in Lesson 1, we are going to continue to use sequential process synthesis methodology to build our Chemcad simulation for this conceptual design. Now, let us look at the stoichiometry of the gasification reaction. The gasifier reacts the biomass with water at high temperature to produce synthesis gas, which is a mixture of CO, CO2, and H2. The gasification reaction can be expressed as this chemical reaction here. To use this reaction in Chemcad simulation, we need to have the stoichiometry fully specified, that is, we need to find coefficients A, B, C and D. At the same time, we need to make sure that the ratio of CO2 to CO is 1.1, as specified. This means that C divided by B equals 1.1. This ratio means that for every 1 mole, or atom of carbon that goes to making CO, 1.1 moles or atoms will go to making CO2. Another way of looking at it is that, for every 2.1 carbons that reacts, 1 will form CO, and 1.1 will form CO2. If you have 22 carbons in reactants, like we have with our biomass, we can use the carbon balance ratios to calculate the values of stoichiometric coefficients, C and B, like we have done here. If you want more clarification, these calculations are explained in detail in Lesson 1. We can further confirm that the ratio of CO2 to CO is 1.1, as required in the problem specifications. Next, we can do the oxygen atom balance to find how much water will be needed, that is, we will calculate the value of the stoichiometric coefficient, A. Then, we can do the hydrogen atom balance to find how much hydrogen will be produced, that is, we will calculate the value of the stoichiometric coefficient, d. Let me state this here again. If you do not understand these calculations, please refer to Lesson 1, where we carefully and slowly take you through these calculations. Now we have a balanced chemical reaction, we can proceed to simulate the gasifier in Chemcad, as specified in the problem statement. We will use a stoichiometric reactor with the reaction, as given here, and the specified reaction temperature and pressure. It is important point to note here that we can see from the stoichiometry that the ratio of H2 to CO is 3.677, which is much higher than the required value of 2 for the methanol synthesis reaction. To start off, let us use a feed flow rate 1 kmol per hour for biomass. We will come back to adjust this value to produce the required capacity once the entire flow sheet is complete. The gasifier pressure is given as 20 bar. If we were using overall mass balance process synthesis approach, as I prefer in most cases, the throughput would be calculated from the beginning. For this sequential process synthesis approach, we will use mass ratios after we have completed the simulation to scale our process to the required capacities. We will come back to this in later lessons. For feed flow rate of 1 kmol per hour of biomass, you know from stoichiometry that you will need 24.5238 kmol per hour of steam. Let us supply saturated steam to the gasifier at the gasifier pressure of 20 bar. The biomass, which is lignin H, will be supplied at temperature of 20 degrees Celsius to the gasifier. Thank you very much for studying with Tutor.me Open College. Please click subscribe so that you are kept updated with new learning material as it is being updated. If you like this video, also, please click like so that the video is recommended to other learners such as yourself.